Step 15, we're going to learn how to transform functions. Before we begin with that, we need to think about some of our most common, famous functions that we've all been learning about and studying about, and some that we are going to continue to learn about in future studies. We've talked a lot about the linear function. In Unit 3, we talked about the quadratic function. We've touched on the cubic function in Unit 4. And back in Unit 2, we talked a little bit about the absolute value function. These are considered parent functions. As you can see, they're the most basic type of each type of function. For instance, right here, f of x equals x squared is the most basic quadratic function. It has 0, 0 as its vertex. It hasn't been stretched or moved in any way around the coordinate grid. It is basically your home base function, if you want to think of it that way. All functions could be transformed back to the parent function by applying a bunch of various transformations. And we're going to look at each type of transformation individually. Some other parent functions that we are going to just touch on are the reciprocal parent function, exponential, logarithmic, and square root. Now we're not going to get too in depth because once we get to Unit 5, which is right after this unit, we are going to study the transformations of these functions in depth as we study these functions. And then finally, we have three very famous trig functions, sine, cosine, and tangent. And again, we'll touch on this, but we're not going to study these functions in depth right now because we will study them more when we get to Unit 8. So in general, if we have a function, there are so many things we can do to the function. We can subtract a number from x or add a number inside the parentheses. We could add a number outside or subtract a number outside. We could multiply the function by some number. We could change that number to a negative. Doing all of these things create different effects. So if the value of a is greater than 1, it's going to stretch the parent function. And if the value of a is between 0 and 1, it's going to compress the parent function. So it's going to change the shape of the parent function graph. If a is negative, it's going to reflect over the x-axis. I'm going to kind of put that right before it so that we can pretend that that's a negative. It's going to reflect in the x-axis. If we have a number k that is added, it will move it up. And if we subtract k, it will move down. And then finally, we have our horizontal translations. If we have x minus some number, it's going to move right. And if we have x plus a number, it's going to move left. That's kind of the opposite of what you'd think. You might have thought, oh, I think she said that backwards. I actually didn't. And we will explain it in greater detail as we explore these functions. Here it is all mapped out in a concept summary. So you have all of the information you need. But we're going to look at these individually and take a closer look at what it means exactly. So let's flip over to some delta math. Right here it says try to get this black quadratic to line up on the dotted orange quadratic. Well, remember, putting a negative before the function makes it reflect over the x-axis. So if I change it to negative, you see it kind of flips. Well, that doesn't help because I wanted it to open up and now it's opening down. So I'm going to change it back. We did not need to do that. One thing that we haven't talked about yet, if the negative is before the x but within the function, for instance, if it was inside the parentheses here, being squared, that makes this function reflect over the y-axis. Now with a quadratic that's symmetric, you're not going to be able to really tell, but watch the animation. See how it reflects and flips over? But it doesn't really change anything, so we'll leave it as it is. Next, let's look at this second number here, right here. Actually, the second number in the parentheses, or the second blank. Let's try to figure out how much I have to move to the right. So I want to look at the vertex of the black quadratic and the vertex of the dotted orange quadratic. I need to move one space to the right. Now remember, when you're doing this inside the function, inside the parentheses, you're going to do the opposite. So you would think it would make sense to say +1. So let's try that. When I just add 1, it slides to the left, which is the opposite of what I wanted. So I need to type -1 so that it slides to the right. Next, I need to get this black parabola to go up 6 units. And moving up and down is very intuitive. If you want to go up, you add 6. If you want to go down, you subtract 6. And there we have it. Let's try another one. Okay, this is just a polynomial function. We're trying to get this lined up. So it looks like we need to probably take this low point and slide it over to the right 4 units. So I'm going to do a subtract 4 right here just to try to get this thing lined up. Alright, that worked pretty well. Next we need to go up 3 units. So let's add 3 and see if we land on, and we do. We didn't need to do any reflecting. Alright, how about this one? Trying to get this function onto the orange dotted function. Well, I know that both ends are pointing up in the dotted orange function, so let's reflect this over the x-axis by doing a negative. Wonderful. Okay, next I can see that this low part, this minimum right here, would probably line up here if I could slide it 3 units left and 1 unit up. So I'm going to add 3 to go left, because remember it's the opposite of what you'd think. And then I'm going to add 1 to move up. Alright, another way we can look at this is with Desmos. Notice here we have the quadratic parent function. We have placeholders for the factor a that stretches or compresses this. We have the factor of h that moves it left and right, and we have the factor of k that moves it up and down. You can see that as I slide these, as I make k larger, by adding a bigger number, it goes higher and higher. And if I make k smaller or negative, it goes down. You can see that moving h, when h is positive, it does go to the right, but think about what that means. That means x minus 3.6. So it looks like we've subtracted a number from x from the formula. That makes it go right. And when it's negative, x plus negative 4.8, it goes to the left. And then finally, if a gets larger than 1, I'm stretching this parabola and making it skinnier. If a is a fraction between 0 and 1, it flattens and gets a little bit more compressed, like I'm smushing it into the x-axis. Until I get to negative numbers, then it reflects over the x-axis. So that's just a little bit of an introduction into some of these parent functions. We will practice with a lot of examples and a lot of delta math and con, making sure that we can properly transform the main parent functions. Like I said, we will likely focus on reciprocal, exponential, logarithmic, and square root in Unit 5. However, you may encounter some of these in your online practice. and you're going to treat them the same way that we've done some of the other examples. See if we can find one in Delta that is from Unit 5 actually. Alright, this one would be from Unit 5. Again, if you look at our parent function list, this is an exponential function. So we're trying to get this to line up on the orange part. So we do need to reflect it, but we want to reflect it not over the x-axis. If I put a negative here, that doesn't help me. I need to reflect it over the y-axis by putting a negative right here. Do you see how that changed the function up here? 2 to the negative x. I put the negative next to the x, not in front of the function, but next to the x. Now I need to make it go up a little bit. It looks like it needs to go up 2 units. So let's add 2 on the end. See how it adds 2 to the end? And that's all it took to get it where we needed. Here is a radical function. Again, I need to reflect it over x. So I'm going to reflect it down here. You can see that I have y equals negative radical x now. I need to slide it over here to the left by adding 5. So x plus 5 under the radical makes it go left. But I also need it to slide down. So I need to go down 1, minus 1 at the end, and it slides down. You can see that this is a transformation of the parent function y equals radical x. It's gone 5 units left, 1 unit down, and it's reflected across the x-axis. Now we haven't talked much about our linear parent function, the function y equals x. That's when m is equal to 1 and b is equal to 0. This is the line y equals x, that's the parent function. The reason I saved this one for the end, you would think it would be the easiest one to start with, as it's a very simple function. It's almost too simple. It's hard to see some of the transformations taking place. For instance, m plays the role of the letter a. It's the number before the function that we're multiplying by. When a, or in this case m, is bigger than 1, it gets stretched or pulled upward, and when m is a fraction less than 1, it flattens it, and eventually, if it turns negative, this line reflects over the x-axis. So it still does the same things that our absolute value and our quadratic and our cubic functions do. It just is going to look a little different. Same thing with the b value. It's very hard to have an h value and a k value when we're talking about the linear function. If you think about the b as being the k value, when you add a number, this line goes up. When you subtract a number, this line goes down. But you could also follow this point on the x-axis and think about this b value as our h value. If I'm subtracting something from x, it's going to move to the left. And if I'm adding a number, I think I said that backwards already. If I subtract a number, it goes to the right. And if I add a number, it will go to the left. You might say, well, how can you tell if it's going left or if it's going up? With a linear function, it's very difficult to make that determination, which is why I saved them for the end, because it can be challenging. Finally, I just want to give you a couple examples of functions. F of x equals negative x minus 3, the quantity squared, plus 7. And I would like for you to state what the transformations are. So we're going to look at it piece by piece by piece. I'll try to be consistent with my colors. Green, yellow, blue. let's take a look at this. Yellow is my number right here. This is my H value. This is my K value. This is my A value. And this number right here tells me if it reflects or not. So we need to comment on all 4 of these, starting with the negative. The negative right here means that this function reflects over the x-axis. This green number right here, you can't even see it, it's just the number 1. So that has no effect, no change. If it were bigger than 1, it would stretch. If it was less than 1 but greater than 0, it would compress. This means that we move 3 units. Remember, -3 makes you think left, but it's actually to the right. And then finally, this last piece is telling us that we shift 7 units up because it's positive. Let's try another one. Let's try a cubic one. Let's do g of x equals x plus 6 the quantity cubed minus 2, and we'll put a 1/2 here. So again, comparing these numbers individually, the 1/2 is going to be a compression. By a factor of 1/2. And then we'll look inside here, adding 6. This means we've shifted left 6 units. And finally, this is shifted down 2 units.